Okay, today we're gonna start our lecture 2, titled Early Memory Management Systems. So this is basically just talk about your how does operating system operate your RAM or your hardware RAM. So they have like two modules. One is hardware modules RAM and one is operating system. So today we're gonna learn how operating system handles all the jobs in your RAM, random access memory. So, management of main memory is critical. So, yes, without RAM, your computer cannot run. Because they don't have a memory. Instruction from CPU will always instruction from CPU will always refer to the main memory or cache memory, but it still is a RAM. The performance of the entire system has been directly dependent on two things: how much memory is available, how is the optimization while jobs are being processed. So RAM, if you want to buy a PC or laptop, you always now it's like minimum. I think you have to have 8 GB of RAM, I guess, or maybe 4 MB. But usually now, you for the new computer applications, of course, if you are gamers, you need much more RAM with a CPU. I mean, for you must need both CPU and GPU. So I think now the minimum acceptable RAM is 8 GB. So this chapter introduced the memory manager RAM and the core memory primary storage. So you have four types of memory allocation schemes. Okay, how are the jobs allocated in your memory? So you have a single user systems, fixed partition, dynamic partition, and relocatable dynamic partitions. So basically, a relocatable dynamic partition is same with the dynamic partition, but it's you can adjust it. You can adjust it or more advanced algorithm of the dynamic partitions. These early memory management systems are seldom
I'm sorry,
used by.
Doctor, you're muted.
Sorry. Someone in the meeting mute you.
Excuse me, Doctor.
Okay. Can you see? Can you see? Can hear you now?
Yes,
Yes.
you can hear
Okay.
you.
Okay. Someone in the meeting mute me, but never mind. Okay. These early memory management schemes are seldom used by today's OS, but are important to study because each one introduces fundamental concepts that help memory management evolve. Now they are more like a parallel one, more advanced one, but all this is a fundamental. You cannot understand the advanced before you understand the fundamentals. You must know the fundamentals, how like this early memory management system in the operating in the OS functions, so that you can learn how is the advanced way of the memory management in like newer in like a newer OS. So type of memory allocation scheme, you have single user contiguous schemes, fixed partition, dynamic partition, relocatable dynamic. Contiguous meaning that it's just side by side, okay? Side by side. If like in the disease we take about COVID-19, if you are near to the person that have a COVID-19, you are contiguous, meaning side by side, a nearby, just beside that. In other terms, okay? So you like in the main memory, this is a block 1, this is a block 2, so this is contagious. Just to give you some terms to for you to understand some OS terms. Okay, so single user contiguous schemes. So this basically a serial one, commercial level 1940s and 50s. Very old technology, but this is the most fundamental that you can get. Each program was loaded in its entirety into memory and allocated as much contiguous memory space allocated as it needed. So if the program was too large and didn't fit the available memory space, it couldn't be executed. So you have basically, if you have a job, you will occupy. I mean, if like jobs, this is like, let's say you have 100 kilobytes. So let's say jobs is like 50 kilobytes. So they will use here 50 kilobytes, and others are unused or wasted. If like jobs like 200, if the jobs enter 200 kilobyte, so it cannot fit the memory. Okay, if the program was too large, didn't fit the memory, it couldn't be executed. So this job will never be executed because the memory space is not enough. That's why in modern one, jobs must be job is job is separated by processes, and processes is separated by thread. So make it a small chunk of jobs, we call a process. In each process you can chunk it even smaller, and we call it thread. Although early computer was physically large, they had a very little memory. They are as big as your, I think as big as your like lab room or half of it, but they are very little memory. I think 4 kilobyte, 2 kilobyte or something. Kilobyte, not a gigabyte like us now. Computers only finite amount of memory. So if program doesn't fit, then either the size of memory must be increased or the program must be modified, making it smaller. And one, if you talk about single user, so this is the, like say 100K. So if like job one, 10K. So this one is job one 10K. They have to wait job one finish first, and then job two, let's say job two, have 50K. Whatever, if you have to wait until job one finish, until you before job two can enter the memory. So this is like a waste, because this is serial. No matter how small is the job, the current job is, the next jobs cannot enter the memory. Okay, because you have 100K, and then job one 10K, job two 20K. Sorry, 20. Sorry, job two is 25K. So like, if like job one is currently processed by the memory, job two cannot enter the memory because you have to wait until job one finish. So this is very unused portion, or unused unused block, which is wasted. It's not efficient memory management. So the program, then either the size of memory must be increased or the program must be modified, making it smaller. Using methods that allow program segments partitions made to the program to be overlaid. You can do that by transfer segment of program from secondary storage into main memory for execution. Secondary storage meaning that all your like hard disk, CD, I mean, who use CD? Your hard disk drive, or now solid state drive, SSD, solid state drive, or maybe your USB or whatever. This is your secondary storage, not a RAM. This is non-volatile memory. And then the transfer of program from execution into memory for execution, or two or more segments take turns occupying the same memory locations. Two or more segments take turns occupying the same memory locations. So how it works? Job program is loaded entirely into the memory and is allocated as much contiguous space in the memory as needed. If program fits, execute, else end. So let's say this one job one, enter. So you have like 100K or something. This is the space. So job one 20K. So this is job one, occupying space of this blocks. Job one 20K. If program fits, execute. So job one 20K, so execute, else end. If like job one, this one is a case one. If a case two, job one is 150K. So because the memory size is 100K, so job one for the case two is 150K. So it will just end the program. It will not execute. If a program doesn't fit, then either the size of memory must be increased or the program must be modified. That's the only solution. So you have here this one, operating system, job one 30K. You have 10 and 40K, because 10 40K, let's say this is remaining say this is 200, let's say this is 150, so you still have 100k. So whatever is a single, this one, any jobs must wait a job one to finish first, regardless how small or big the job one. So this remainder of memory is unused, which is really wasted or not an efficient memory management. It is a non-network environment allocated to each user. So this is a single PC. Access to all available memory for each job, and jobs are processed sequentially, one after another, sequentially or serial. To allocate memory, memory manager will evaluate the incoming job for its size, whether it fills the memory space or not. So this is a very simple algorithm. If it is load into memory, if not, reject it and evaluate the next coming process. So monitor the occupied memory space. When the resident jobs end its execution and no longer needs to be in memory, indicate that the entire amount of memory space is now available and return to step 1. Evaluating the next incoming job. So like job 1, go back to the, so job 1 is 30k, job 2 is 50k. So job 1 if job 1 finish, it will go, job 1 finish. So this block of memory will be deallocated and job 2 will enter the memory. So the major problem of this algorithm is simple, but it doesn't support multi-programming. You cannot do like two jobs or two programs at one time. Meaning that you cannot run like you cannot run your, let's say what, your PDF with your Microsoft Word, or you cannot run your, or internet, if you open Google Chrome, you can open others, you can open Word, you cannot do a multitasking or multi-programming. So this is uh, one of the weakness, is a major drawback of the single user. So algorithm store first memory location into base register for memory protection. Step program counter, it keeps track of memory space used by the program, equal to either first memory location. Read first instruction of program. Increment program counter by number of bytes in instruction. So this is just algorithm. Has the last instruction been reached? If yes, then stop loading the program. If no, then continue with step 6. If yes, if no, then continue with step 7. Load instruction in memory. Good. This is just algorithm. I think this is from the textbooks. Yeah, this is just algorithm. So again, this is the advantage. No support multi-programming or networking. You can only run one program at a time. It can handle only one job at a time. This configuration was first used in research institutions but proved unacceptable for the business community. So it was not going to spend almost 200,000 for equipment that could be used by only one person at a time. So early PC, is what? Early computer, not PC. PC is 79, 1979, 1980, something like that. So the first computer, I mean the earlier, the the early computer cost you like a massive 200,000 in dollars. Now you can buy a house for that, but it can only use by one person at a time, which is not really useful, and very small memory. So the amount of work performed by the manager is minimal. Memory manager is, I mean, the memory manager just look at the size of the jobs. If the jobs if job is smaller or same size as the memory, it will be executed. But if the jobs are bigger than memory, it cannot be executed or stored in the memory. Only two hardware items are needed: a register to store the base address, and accumulator to keep track of the size of program as being read into memory. So only two hardware items: register and accumulator. Once the program is entirely loaded into memory, it remains there until execution is complete, either through normal termination or by intervention. So by normal termination, meaning that your job already finished, or by intervention of OS, meaning that if you need to do something, you don't want this, you want to cancel the job, the OS can do that. Okay, now we go to the second one, the fixed partitions. The first attempt to follow multi-programming use fixed partitions or static partitions within a main memory. One partition for each job, meaning that if you have a memory here, you have here partition 1, partition 2, partition 3, and so on. One partition for each job. The size of each partition was designated when the system was powered on. So it depends. When the system was first powered on, it depends on the incoming jobs of the first one. The incoming jobs of the first batch of jobs input. Okay, so like let's say at the same time, job 1, job 2, job 3, and job 4. So like job 1, job 2, job 3, job 4 coming at the same time. So it will be allocated based on the size of these jobs. Each partition can only be reconfigured when the system was shut down, meaning that the first batch J1, J2, J3, J4 will determine the size of the each block in the main memory. We will go to the example in the next slide. Once the system was in operation, the partition size remains static, fixed partition. So because RAM, remember RAM is a volatile memory. If the machine or PC is shut down, so all the block memory will be removed. So when you power on, it will be a fresher memories. So it will go again to the cycle of the instructions. Introduce protection of the job's memory space. Once partition was assigned to a job, no other job could be allowed to enter its boundaries, either accidentally or intentionally. So once partition was assigned, no other job could be allowed to enter its boundaries. So we will go to the diagram example after this. It's not a problem single user contiguous allocation scheme. Single user just like one jobs at a time, regardless small or big. Fixed partition is more flexible than a single user scheme because it allows several programs to be in memory at the same time. So it was the first scheme to support the multi-programming or multi-function or multitasking. Fixed partition still requires that the entire program to be stored contiguously and in memory from the beginning to the end of execution. Like I said, contiguously meaning that you have a side by side following in sequence. This block 1, block 2, block 3, and block 4, and so on. So from beginning to end of its execution still requires that the entire program be stored contiguously. Okay, we will see that. Is it that? In order to allocate memory spaces to jobs, the OS memory manager must keep a table which shows each memory partition size, its address. Okay, a memory got address. So this is the address one, address. So each of the line they got address. Okay. If you learn microprocessor or machine language or assembly language, you will learn how to program the CPU. Or okay, its address, its access restrictions, and its current status, free or busy. Free means that the block is free. You can enter any jobs can enter. Any jobs can enter if it fits the smaller or same size with the block. Or busy. Now the current partition is executing a job. As each job terminates, the status of its memory partition is changed from busy to free, so an incoming job can be assigned to that partition. So if job terminates, the memory block will deallocate the memory, and the particular block will become free for any new incoming jobs to enter. Okay, a memory manager allocates a memory space. So use a table. So partition size 100K, memory address is 200K, access job 1. So okay, memory address is just like your postcode, memory address, just like your postcode or your house number or something. So partition size 25K, job 4, 25K free, 50K busy. So okay, this is a simplified fixed partition memory table with a free partition shader. So you have a job 1, job 2, and job 3, and job 4. 4 jobs, job 1, job 1, job 2, job 3, and job 4. You have job 1 is partition, this is a partition size, is a memory address. So memory address is not really related to the, kind of related, but kind of related with the partition size, but it can be like any numbers. But at the moment, just ignore the memory address, just a room number. It doesn't integrate with the partition size at this moment. So let's say job 1, what's the memory address? Job 1, 200K. So let's say job 1 memory address is 200K. Job 2 is 300. Sorry. Partition 300K. So no, this is not depend on the job. 300K. 325K. This one is 325K. 325K. And this is 50K. Sorry, this is 350K. 350K. So this is the address. Wait. So this is just the address. Starting address. Starting address for each location, 300K. Okay, now we go for the job 1. Job 1, 30K. Fixed partition. Job 1 will go directly to the partition 1. Okay, 100K. Job 2, 50K. Job 2, 50K will directly go to the partition 4, 50K. Job 3, 30K. Okay, block 1 and partition 1, partition 1 and partition 4 already occupied. So they left partition 2 and partition 3. So if job 2, 50K, partition 2 and partition 3 cannot accommodate job number 2. So job number, job 3. So job number 2 is going to partition 4. Job 3, 30K, cannot, partition 2, partition cannot accommodate the job number 3, 30K. Sorry for that. So job 3 has to wait. And job 4, 25K, it can go either partition 2, partition 3. So it follow the sequence. So it will go to the partition 2 first. So this is unused. So this internal fragmentation, this is all we call internal fragmentation. This is internal fragmentation. So sorry, this is not the this okay. Wait. Sorry, this is both are unused. Both are unused, but like if it is still in the partition, meaning that the partition 1 is 100K, but the job only 30K, this 70K unused is called the internal fragmentation. For this one, partition 3 is unused because job 3 is 30K, cannot fit 25K, so it is unused. This is not internal fragmentation, but still it is a waste of space with waste of memory block. So this is a fixed partition. So let's say if job 3 have to wait either job 1, either job 1 or job 2 finish. If job 1 or job 2 finish, the job 3 will go to the partition 1 or partition 4, okay, for it to execute or for the blocks to become busy. So what's the disadvantage? You can see that job 3 has to wait. Here job 3 has to wait. Although the unused memory is, if like you combine 25K plus 70K, 25 to 70, 25 is like 125k of free space memory, but job 3 has to wait because partition 1 occupied, partition 4 occupied, partition 2 and partition 3 cannot accommodate job 3. So disadvantage is okay, of course a scheme works well if all jobs run into system are of the same size. Of the same size is easy. But of course in the real world it's not the same size. Some applications are heavy, some applications are very light. If the partition sizes are too small, larger jobs will be rejected if they are too big to fit into larger partitions. Large job will wait for the if the large partitions are busy. Large job may have a longer turnaround time as they wait for free partition of sufficient size or maybe may never run. It's stuck there in the CPU, cannot go into the memory. So if the partition size are too big, memory is wasted. If a job does not occupy the entire partition, the unused memory in the partition will remain idle. So we call internal fragmentation. It cannot be given to another job because each partition allocated to only one job at a time. So partition usage of this partition and the concentration of unused space within the partition is called internal fragmentation. Okay, if you just to recall, like partition 1 is 100k, but use only 30k. So this segment we call internal fragmentation. Okay, and it's a major drawback to a fixed partition memory allocation scheme. So this internal fragmentation is unused memory which is wasted, not an efficient memory management. Now we go to the third one, the dynamic partitions. With dynamic partitions, available memory is still kept in contiguous blocks, but jobs are given only as much memory as they request when they are loaded for processing. So this is what, as the name suggests, the dynamic partitions, it become dynamic. It will allocate memory based on the job size. A dynamic partition scheme fully utilizes memory when the first jobs are loaded. Okay, when the first job are loaded, they will fully utilize the memory. As the new jobs enter the system, they are not the same size as those that just vacate the memory. They are fit into the available spaces on a priority basis. First come, first serve priority. So if you know, like you are queuing to, you have a first come, first serve, last come, first serve, round robin, and so on. So this is all the algorithm for the queuing, or the we call it a queuing theory. So dynamic partition is based on the first come, first serve priority. The subsequent allocation of memory creates fragments of free memory between blocks of allocated memory, or we call it external fragmentation. So you see that examples after this. So less memory go to waste, but it's not as wasted as a fixed partition. So this is a first come, first serve, FIFS, first come, first serve. So job 1, 10k, job 2, 15k, job 3, 20k, and job 4, 50k. So operating system will take about 10k. Okay, job 1, 10k, fix, job 1 will go into here, 10k, job 2, 15k, job 3, 20k, and job 4, 50k. Initial job and entry memory allocation. Okay. And then for the second one, this is A. So they all processing, entered, stored, and then job 1 ends, and the memory deallocates the partition block. And job 4 also ends, though the memory deallocates this partition. So job 5 arrive 5k and job 6 30k. So job 5 will go into the first partition of job 1, and job 6 30k arrive on the partition. Job 6 30k will arrive on that after job 3 in the partition 4. Okay, so job 1 5k and job 6 is 30k. So job 1 partition last time it was 10k. Okay, 10k. And job 4 last time partition is 50k. So this one use a 20k unused, and this one is 5k unused. So let's say job 3 ends. After job 3 finish, job 3 ends. So it free this one. So job 7, 10K arrive. So straight away go to this one. This partition, job 7. Job A is 30K. Job 8 is 30K. So there are no 30K available memory. Okay. This is 20K. This is 20K, sorry. This is 5K. This is 10K. So job 8 have to wait. Although if you combine the unused memory is 5 plus 10 plus 20, 15, 20, 35K, you actually you can accommodate if it is alone based on the free space or unused memory, but job 8 has to wait until one of the slots, like these two slots or these slots finish. Okay, so job 8 has to wait even though there's enough free memory between partitions to accommodate. So like the free partition is 35K, but it's all on the different blocks or different partitions. Job 8 has to wait. So in the system, anything we want to minimize the waiting time, or we just want to minimize or remove wait. Of course, in the actual world, we cannot totally remove waiting, but we try to minimize it. All right. So any system that have to put a waiting time or waiting list too many or too long, it is not a good system. So for both fixed and dynamic memory allocation scheme, the OS might keep lists of each memory allocation, noting which are free and which are busy. As new jobs comes into the system, the free partition must be allocated. So these partitions may be allocated on the basis of first fit memory allocation, first partition fitting the requirements, or best fit memory allocation, smallest partitions fitting the requirements. It is a least wasted space, but it's a slower performance. If you want to talk about the unused memory wasted unused memory, best fit memory allocation have a least wasted space compared to first fit, but it is a slower performance. We will see after this. For both schemes, the memory manager organizes the memory list of the free and used partition either by size or by location. The best fit allocation method keeps the free busy list in order by size, smallest to largest. Makes the best use of memory space. So it has a table, a database, free busy list in order of size, smallest to largest. And the first fit method keeps the free list organized by memory locations, low order memory to high order memory. So this is based on the location. This is based on the size. Okay, best fit size, first fit location. All right. Okay, now we will compare best fit scheme and a first fit scheme. So we have a look first at the first fit scheme. So you have your job list and this is a memory list. So what we draw here a RAM. Okay, we draw the RAM. So partition number, okay, this is OS 10240. This one is 10240. Okay, 10240. The location and the size is 30K. This is size of 30K. And the second one is size of 15K. The third one is the size of 50K. And the last one is size of 30K. So you have here P1, P2, P1, partition 1, partition 2, partition 3, and partition 4. Look at this table. And then here you have location 40960, 40960. And you have here 56320. And you have here 107520. So you have here size is 30k, here size is 15k, and 50k, and 20k. Okay, first fit scheme. Okay, we look at first fit scheme. So job 1 coming first, job 1 10k. You remember the first fit scheme, whenever it find the first partition that can accommodate the job size and the memory size that it requested, it will straight away goes to that partition. So job 1 goes to partition 1. Job 1 is 10k and partition 1 is 30k. So it can accommodate job 1, so job 1 will stay here. Job 1 will stay here and you have an internal fragmentation of 20k. Okay, so job 1 here is 10k. And then coming job 2, job 2 partition 1 already occupied. Job partition 2 is 15k, cannot accommodate job 2, so it will scan the job, it will goes to partition 3. Partition 3 size is 50k and job 2 is 20k, so job 2 can partition 3 can accommodate job 2, so job 2 will select partition 3. So this is job 2. So job 2 is about 20k and you have an internal fragmentation of 30k. And then comes job number 3. Partition 1 occupied. Partition 2 free, but partition 2 is 15k, while job 3 size is 30k, so it will not select partition 2. Partition 3 occupied. Partition 4 is 20k, which cannot accommodate job 3, which is 30k, so job 3 has to wait. Then coming job 4, P1 partition 1 already occupied. Partition 2 is 15k and job 4 is 10k. Partition 2 free, so job 4 will go to partition 2. So you have here job 4, which is size of 10k and the internal fragmentation of 5k. So this is the first fit scheme. Alright, this is the first fit scheme. So job 3 has to wait. Job 3 has to wait in either P1 finish or P3 finish, because job 3 is 30k. Alright, so job 3 has to wait. So even although there are 75k or unused memory space, or the combination of internal fragmentation, job 3 cannot be inserted into the memory, okay, in any of the partition. Now we look at the best fit scheme. So this again, this is the OS. See, this is the OS. So this is a partition 1, 10240, 10240, and this is the job. This is the partition 2, which is 40960, 40960. Partition 1 and partition 2, and partition 3 is 56320, partition 3, and partition 4 is 107.107.520, which is partition 4. Okay, the best fit scheme. Job number 1 is 10k, so it will scan all the partition. Okay, job 1 P1 is 10k. Sorry, P1 is 30k, P2 is 15k, P3 is 50k, and P4 is 20k, the size of the partition. So job 1 10k, it will scan every partition, so it can fix either P1, P2, P3 or P4. It can fix any partitions, but because the best fit scheme, it will select the closest fitting free partition. So you have here 30k, 15k, 50, so it will select a partition number 2. Okay, partition number 2. So job 1 will be, because 15k is the best, the closest fitting free partition. Okay, the best fit. 15k just best fit. So because 10k, so you have you wasted only 5k internal fragmentation. Okay, now coming job 2, 20k. So it can fit P1, P3 or P4. So because it's 20k and P4 also 20k, so job 2 will go to here, partition number 4, because the best fit scheme. So it doesn't have any best fit scheme, not scream. Okay, sorry. Job 2 is 20k, fit nicely on partition 4, so there is no internal fragmentation. So come job number 3. Job number 3 can fit partition 1 or partition 3. It's 30k. So job 3 will select P1 because it can fit nicely, just nice, 30k, 30k. And job 4 will go to the partition number 3. So overall you have okay, overall you have 5 plus 40, you have 50 50 kilobytes, 50 kilobytes, okay, 50 kilobytes wasted space, but it is still better than the first fit scheme, which is 75k. Okay, so this scheme use memory more efficiently, but it's a slower to implement. Why? Because you have to scan every partition and select the best one that fit the memory size and doesn't waste any internal fragmentations. So this is the best fit scheme. So algorithm for first fit, assume memory manager keeps two lists, one for free memory blocks and one for busy memory blocks. The operation consists of a simple loop that compares the size of each job to the size of each memory block until a block is found that is large enough to fit the job. So whichever partition like these jobs coming in, it, it will search which of the partition that can fit him regardless of how big is the partition. Okay, let's say job 1 is 20k. Let's say the first allocated block is, let's say, 100k. If job 1 go to the if job 1 meet the first partition, it will straight away go to the 100k, although it jobs only 20k. This is for the first fit. The job is stored into that block of memory and the memory move out the loop to fetch the next job from the entry queue. If the entire list is searched in vain, then the job is placed into a waiting queue. So the job is too big to fit in any of the memory location, any memory partition, it will goes into the waiting queue. The memory manager then fetches the next job and repeats the process. uh So these two snapshots of memory show the status of each. Okay, this is before the request. You can see that this is a big beginning address 4755225667855, and this is the memory location. This is a memory location. This is a memory block size. Okay, block size, the partition size. Okay, this is the partition size. You just draw this one, and this is like 105, and so on. The last one is 1000. Okay, and this is like 47755225, and this one is 24500. So this is the way you draw the way you convert to the memory diagram. So before request you have okay, this is before request. Okay, a request block of 200 spaces has just been okay to the memory manager. So request block of 200 spaces has just begun to the memory manager. Okay, 200. If you go for the first fit, okay, this is the first fit. Okay, the keyword is first fit. If like the 200 job size is 200, which one it will go first? First, it will search this one, doesn't fit. Second, it will go this one, doesn't fit. Third will go this one. Okay, 600, this one fit. So 600, so this is before request. So when it requests 6785, it occupies the 200 size of this memory partitions. So what you have here, It will request here, this is a 200, 200 6785, and this one is 6985. Okay, after request the memory block size, this is the status of each memory before and after the request is made using the first fit algorithm. So you have a 400 spaces of 400 size, 400 kilobytes of size, 400 kilobytes of size, free spaces, because you only use 200 memory size of 200. So in the first fit, it will search one by one until it find the partition that can fit its job size. So this one, 6785 200, 6785 plus 200, 6985. So 6985 left a 400 unused memory space. So this is the first fit algorithm. We go to the algorithm for best fit. The goal is to find the smallest memory block into which the job will fit. The entire table must be searched before the allocation can be made. Okay, different from the first fit. The first fit doesn't the first fit, of course, the first fit will check one by one first according to the sequence, and whenever it meets with the partition that can fit its size, it will select that. That's it. So in this case, it will select like three, it will check three partitions. Partitions number three can fit its job, so it will select partition number three without searching all this, remaining partition. But for best fit, the entire table must be searched before the allocation can be made, because the memory blocks are physically stored in the sequence according to the location in the memory. The memory blocks are physically stored in the sequence, okay, according to their location in the memory. So let's say this is the best fit. This is the best fit algorithm. Job has 200 in size. So first it search this one, search this one. Okay, search this one. Okay, one of it. Okay, but still it search the entire table. This one, okay. This one, okay as well. This one is okay as well. This one is okay as well. So it search the entire table. But which one is the best fit? The memory, which partition best fit the job size? Of course, this 7600, because 7 is 205, which is only five, only like five. The job size of 5 kilobytes is wasted. Rather than select this one is like 400, this one is 3850, this one is 30, and this one is 800. So this is the less memory wasted, least memory wasted. So this is the best fit algorithm. We search entire table. So from this one 7600, so the new block will be this one is 7600, this one will be 7800. So this the 200 in size, so this become, sorry, it's supposed to be small one. So this one use 200, and 7OM only 5 kilobytes unused memory space left. So this is the best fit algorithm. First fit faster, but it wastes a lot of memory. Best fit is have a best memory size management, but it's a slower. So first fit size wasted but faster. Sorry, faster, correct? Best fit least size wasted but slower performance. Okay. Also, okay, best fit. best fit versus first fit is the is the most probably two of the most popular algorithm that if you want to use if you want to use in the dynamic partitions. So there is also like others algorithms available like next fit, start searching from the last allocated block for next wave block when the new job arrives. Worst fit is opposite of best fit. Allocate largest free available block to a new job. Okay, largest free available block to a new job. So let's say the job is only 5k size, and then let's say you have a three partition. One is 10, one is 100, one is 200. Worst fit will select the 200. Okay, allocate largest free available block to a new job. To a new job. Good way to explore theory of memory allocation. This is just for you to test. It's not really used in OS, except you want to do a research, you want to test. Not best choice for actual system, definitely. So there eventually comes a time when memory space must be released or deallocated. So like deallocated meaning that the job's already finished process, and then you want to remove it from the memory. For a fixed partition system, when the jobs is completed, the memory manager reset the status of the memory blocks where the jobs was stored to free. This for fixed partition. Any code may be used. Example code, binary values with 0 indicating free and 1 indicating busy. So 0 or 1, something like that. The fixed partition. For dynamic partitions, a more complex algorithm is used because the algorithm tries to combine free areas of memory whenever possible. Okay, so this is a dynamic partition deallocation. The system must be prepared for three alternative solutions. Case 1, when the block to be deallocated is adjacent to another free block. When the blocks, case 2, when the blocks to be deallocated is between two free blocks. Okay, this one, when the block to be is adjacent to another free block. So this one is busy and this one is free. So case 2, when the block to be deallocated is between two free blocks. So this one is free, this one is busy, and this one is free. So this busy partition, this busy memory block that will be soon deallocated is located in between two free blocks, or this one uh, allocated adjacent to another free block. And case 3, when the block is to be deallocated, is isolated from other free blocks. So it will meaning it's all busy. It's not adjacent to any free or located between two free blocks. Case 1, joining two free blocks. Using the deallocation algorithm, the system sees that the memory to be released is next to a free memory block, location 7800. Uh, I think it refers to which one is refers to it. 700 best. So 7,600. So 7,600. I think on this example 7,600. To be released is next to a free memory block location 7,800. So 7,600, 200, and 7,800 is 5, something like that. Okay, this one is free, this one is busy. Memory authority next to free memory block location 7,800. The list must be changed to reflect must be changed to reflect the starting address of the new free block 7600, which was the address of the first instruction of the job that just released this block. In addition, the memory block size for this new free space must be changed to show its new size, which is a combined total of two free partition, 200 and 200 plus 5. So remember, this one is doesn't matter whether it's a free fit or best fit. We ignore that one first. So this one is like the current, the original free list. Now at the location of 7600, where 200k of job size is processed. Now it's become busy. Okay, 700 is 5 here. So they actually indicate the free memory block that is adjacent to the soon to be free. Soon to be free memory block. The job size is 200 and beginning allocation 7600. Okay. This one 7600, 7800, 200 and 5. This one is busy process or something. Okay. So this one is a free. This is the free list. So after this is the free of the actually indicate the location where changes were made to the free memory block. So after the job has been finished or processed, so you want to clear the memory block. Uh, so if like this 200 already free, meaning finished, so you just combine this one 205 beginning at the address location of 7600. So before this 7600 is busy after finish job processing and stuff, it will become free again with 205, the original size of the memory, the original memory block size at the location 7600 become free. Case 2, joining three free blocks. When the deallocated memory space is between two free memory blocks. Using the deallocation algorithm, the system learns that the memory to be deallocated is between two free blocks of memory. The size of three partition 20 plus 20 plus 205 must be combined the total stop with the smallest beginning address 7560. Because the entry location 7600 has been combined with the previous entry, we must empty out this entry. So the entire, okay, this is after the entry allocation 7600 has been combined with the previous entry. We must empty out this entry. Am I mute? No, okay. How to do that? We do that by changing the status to null entry with no beginning address and no memory block size as indicated by an asterisk. This remove the needs to rearrange the list at the expense of memory. So let's say you have here, okay, this busy, but it's like allocated between the 7580. This is busy, okay, this is busy, this is free, and this is free. 7600 just recently free. So you have here busy between two, you have deallocated between two free block, two free blocks, okay. So 20. This is the original free list from the deallocation. That's why you get the two free memory blocks are the adjacent to soon to be free memory blocks. So we have here 7520, 7580 plus 20. So this one is busy and both of these are free. So what you do here, you put just a null entry without the starting and ending address. This is just a null entry. So starting from 7560, you combine all these three, 20, 20, 20 plus 20 plus 205. So you got a 245 with a starting address at 7560, the beginning address. Joining three free blocks. So the third one, the case 3 is deallocating an isolated block. The third alternative is when the space to be deallocated is isolated from other free areas. So using the deallocation algorithm, the system learns that the memory block to be released is not adjacent to any free blocks of memory. It's isolated somewhere else, far away. It is between two other busy areas. The system must search the table for a null entry. When a null entry is found, the beginning memory location of the terminating job is entered into the beginning address column. And the job size is entered under the memory block size column. And the status is changed from a null entry to free, indicated that a new block of memory is available. Okay, we see the this one. This one is the original free list before the allocation. Okay, you have here. Remember this one. And this is a null entry. But the deallocation address is somewhere here. Okay, somewhere between this one and this one. So because 7560 between address 7560 until 10250, this one is free, but this one all busy. Okay, this 7561 until 10249 is busy. Okay, is busy. So this is the job 7805 is 7805, which is here, which is somewhere here. 7805 is busy, 8805 is busy, and 9250 also busy. So 8805 is soon to be free block. It is soon to be free block. So 7805 is the 7560 plus 245, 7805. If you can see here, 750245 is free, but you add 245, 7805, 7805, 7805 until here is busy. Okay, until starting from 7805 until this one. Sorry, 7805. Sorry, yeah, 7805 busy. Starting from 7805. 7560, this one is free, but starting with 7805, this one is busy. So we have here soon to be free is at 8805. The address is 8805. Okay, 8805. So what you do here, the busy, if like you put this one is as a null entry 7805. When it's already deallocated or finished job processing, you mark it as a null entry. And this one from the location of 8805, you put it 445. You have 445 memory spaces already empty or deallocate is already free. Okay, so this okay, we go first here. From here 7805 is busy, 7805 to 10249 is busy. So at the 8805 is soon to be emptied, soon to be free slot. You mark it as a null entry here, and then you put the 8805 and the 445, meaning 445 blocks of memory size that is already free. Okay, this is deallocating an isolated block. Both the fixed and dynamic integration schemes described thus far shared some unacceptable fragmentation characteristic that had to be resolved. Okay, both the fixed and dynamic memory allocation schemes described thus far shared some unacceptable fragmentation characteristic that had to be resolved before the number of blocks waiting to be accepted become unwieldy. So, as one of your friends asking fixed and dynamic memory allocations, this is a fundamental dynamic memory allocations, not really different from the fixed one. In addition, there was a growing need to use all the slivers of the memory often left over, meaning that you have each partition, if each partition have a free space, free memory size that is unused. So the solution to both problem was the development of relocatable dynamic partitions. Relocatable, meaning that you relocate the unused memory space to become one block, or to rearrange the memory block partition. So relocatable dynamic partition. The memory manager relocates programs together all together. This is from the, sorry, this slide is from the books. Relocate programs to gather all of the empty blocks. Gather together all the empty blocks. Okay, meaning that okay, let's say you have a partition. This is partition one, partition two, and partition three. Partition one, maybe you use half of it, half or half. So this is a free. This one is a free. This one is a free. So you want to combine all this regular programs together all the empty blocks and compact them to make one block of memory. So all this free unused unused free is gathered together to compact them to make it one of them, maybe partition 4. Okay, large enough to accommodate some or all the jobs waiting to get in. So this is relocatable dynamic partitions, advanced or dynamic partitions. Okay, the compaction of memory is performed by the OS to reclaim fragmented section of the memory space. To reclaim fragmented section, unused space of the unused memory space. Every program in the memory must be relocated so they are contiguous. So they are set next to each other. Okay. The compaction of every address and every reference to an address within each program. Within each one must be adjusted to account for the program's new location in the memory. So they have every reference to an address within each program must be adjusted to account for the program's new location in memory. So the location, the address location in must be relocated. Hence there is where the relocatable names come from. To account for the new location, a relocation, new location in memory. All other values within the program must be left alone, meaning that all others values within the program, the value is the same, just that the address. Okay, how to say this? All the other values within the program must be left alone. The values are still the same, just the location of the address is changed, meaning that
I'm
let's
sorry,
say,
doctor,
yeah, yeah, okay.
for interrupting you, but um, is it like imagining the physical random access memory, the stick, the slot?
What was it
You
again?
need to
Okay.
you're explaining this. I'm trying to understand what you're trying to explain. And correct me if I'm wrong, but I'm just imagining the physical random access memory, the stick.
Yes, yes, yes. The stick, yep.
Um, so what you're talking about is just the digital way that the operating system is managing the physical part of the
Yes,
random
physical
access
part.
memory, right?
Yep, yep. Yeah, correct.
So
That's
the
correct.
location is changing, but the digital value is not changed in
Yes,
any way.
yes, correct. That's what I'm trying to tell you because let's say if you have what call that you have okay, let's say you are in the house, okay, you are in your old house, you have four cats, you have four pets or four cats, then you move to the new house, you still have four cats, just the location of the house is you move to the new location. This is the real world understanding. Okay, the program must be left alone. All the other values are unchanged, but and values is unchanged, but the address location is changed. Okay, this is the we call the assembly language or machine language in microprocessor, something like that. Okay, this is just some instruction you have. This is the data values 132, 144, 125. Begin move one initial register one, register number one is 0, register number 2 is also 0. So do you want add a plus register 1 to add 1 to register 1 is register 1. So this is we call that, okay, This one is like check or something. If not, go to the loop. Move to register 2, move register to register 3, divide register 3 by 4. So this is just a assembly language microprocessor. You will meet all this. Okay, it's different from the programming language, the software one. This is a machine language or assembly language. You will learn that in the micro P. Is it? I'm not sure whether this is a faculty program microprocessor or not, but in the network department they have you have to take this. Okay, microprocessor. Okay, this is the address. Okay, address 0000 is the value data 132. Okay, 132. Of course, this actually in the this is like the octet or something, octet. But of course, in is a binary, is a 111011. This for simplification, the book shows you 1132. So 001 location is 144. 002 location value is 125, and 003 location is 0010. So 0040 begin initial the register number 1. This one the initial register 2. This one add register 1. Something like that. And then this one jump to loop 006 here. Jump to loop back. Address to be adjusted after relocation. So this is the like this is the, like your assembly language. Okay. Okay, this is snapshot of memory before and after compaction with the operating system of occupying of 10K of memory. Okay, you have a job 1. Okay, you have a job 1, job 4. Job 1, 8K. Job 4. How many partition they have? There's 1, 2, 3, 4, 5. External fragmentation. Okay, this is the external fragmentation. This is a partition 1. Partition 2. I think partition 2. It is a partition 2, partition 3. And partition 4. This is partition 5. So job 1 8K here, job 2 16K, job 2 16K here. Remember this, I think this is the best fit. Job 3, job 4, job 2. Where's job 3? Yeah, okay, job 1, 2, and 4 here is 4 here is 32K. This external fragmentation unused. Job 5 is 48K. Job 6 84K waiting. So what the relocatable dynamic partition means that they relocate all the free space, they move it here. But this address location will be shift up. So this address location of this one will be going to this one, meaning that they're going up. Okay, they're going to the lower memory address. So you have job 6 84K. You combine all the free space, you combine all the free unused free space, and you make another partition here, job 6 84K. So external fragmentation at the beginning has been eliminated, making room for job 6, which after loading show in C. You have 1 2 3 4. Of course you have 1 2 3 4 until they're missing job 3, but just imagine this 1 2 4 5 6. Okay, say job 6 84K. So they remove all the external fragmentation and they combine it into one big partition, so that job 6 84K can be loaded into the main memory. Okay, if you talk about the okay, this is the operating system. This address location. Okay, you have a bound register. first we have a bound register, bound register, and another one is a relocation register. So bound register is a register that program won't try to access memory locations that don't belong to it. Okay, outbound, inbound. Okay, so bound register make sure the program doesn't access memory locations that don't belong to it. Relocation register contains the value that must be added to each address. Okay, must be added to each address reference in the program. So that the system will be able to access the correct memory address after relocation. Relocation register meaning that you relocate the old one to the new one, something like that. Okay, in this particular example, um, within the program at memory location 31744, if you read textbooks, you have there's an instruction looks like load for answer. Okay, load for answer. So this assembly language command as the data value known. The data value known is an answer data be loaded into register number 4. Register number 4. The the register number 4. So the answer value is located at the answer value exact mount is 37, which is located at address 53248. Okay, 53248. So register 4 is like other than bound or other register is a working or computation register. Just like to load the answer, which is 37. Answer is the data 37. So what the location address of 31744 have is a load number load at register 4, value of at the address 53248. Load register number 4. Load register number 4. Register 4 with the value contained at address 53. What the heck? Sorry, I'm sorry. Again. Really sorry for that. One button you can remove all. It's dangerous. Huh? So again, this is a load for answer. And answer is 37 in value. Load for register number 4. What? What is happening here? Wait. I'm not sure what is happening. Suddenly it's like, never mind, we try to. There's some hotkey button that when you enter is remove all, but try to erase it. The previous one appear or something. So load for answer, and then this is register 4 computation register is different from other register. Answer value is 37. Load number 4 at address 31744. So this is the instruction from the machine assembly language. Load at 31744, address location 31744. Load at register 4 the answer. The answer value is 37, which is a load for value content in address 53248. Load register number 4 with value contain at address 53248. So this is the instruction, okay? This is just some instruction for machine language. Load register number 4 with the value answer is 37 with the value contained at address 53248. So this is 3174. Address location 31744. Okay? When they do a relocatable dynamic partitions, okay? Meaning that this one 18K to 30K is around 12K. 12 times 1024 bytes. 12 kilobytes down to 1024 is 122.122.288. Okay, so you move here, everything you move here. From here you move up to a lower memory location, up for 122.122.288 steps, 1228 in size. So here you have a new location of 31744 19456 load 4, and 40960 is 37. Okay, 37, the new one. But the remaining, the 53248 still have the same value 37. Okay, just that it moved to 40960. Okay, so this is all it moved. It is negative because it moved to the lower memory address location register. So all this external fragmentation, which one? This one. This one, all being combined so that you move up a little. You move up to 12288 in size, kilobytes in size. You move location from here. Sorry, here to here. From this one from here to here, meaning that you start at 18 10 18. Here is like 18 18k times 1024 here, 18k times 1024. Everything is moved upwards or to the lower memory address location. So this one is before relocation and after relocation and compaction. We call it compaction. You compact all the external fragmentation or unused memory space in the previous partition into one. Something like that. Relocatable dynamic partitions. Compaction issues. There is also a compaction issues. Actually, is mostly of the workload of the memory. When you increase the work that memory has to do, it's not really a good things. What goes behind the scenes when relocation and compaction take place? What keeps track of how far each job has moved from its original storage area? What lists have to be updated? All this is a compaction issues. RAM has to do more jobs, or OS have to do more jobs. So what lists have to be updated? After relocation and compaction, both the free list and the busy list are updated. Of course, when you move up or you move down, most probably usually is move up to lower memory address. Free list is changed to show the partition for the new block of free memory. Free list is changed to show the partition for new block. The one formed as a result of compaction that will be located in memory starting after the last location used by the last job. The one formed as a result of compaction that will be located in memory starting after the last location used by the last job. Okay, meaning that you move to the new location memory. Busy list is changed to show the new location for all the jobs already in process that were relocated. So if this is all the address location, the address of the memory location is changed. Busy list is changed to show the new location for all the jobs already processed that were relocated. The size haven't changed. Size is not changed. Only the memory address. So there is a memory address and there is a there is a size, memory address. So there is also a special purpose register used for relocation, bound registers used to store the highest or lowest location memory accessible by each program. This ensure that during execution, program won't try to access location that don't belong to it. You always like there's an error. There's an error if you try to access memory not supposed to be accessed. We have some error on that. Relocation register contains the value that must be added to each address reference in the program so that the system will be able to access the correct memory address after relocation. This is a relocation register. Value contain the value that must be added or minus. In this case a minus. Of course, you plus minus is still plus the minus 1228. That must be added to each address reference to get a new location address. If the program isn't relocated, the value 0 is stored in the program's relocation register. So if the program isn't relocated, meaning that it is not changed. So the value 0 is, the relocation register will have a value 0. By compacting and relocating the memory manager, optimize use of memory and thus improve throughput. So this is of course this compaction, the relocation strategy is to improve the throughput and to optimize the memory manager. An unfortunate side effect is that more overhead is incurred than with the two previous memory allocation schemes. Okay, like free fixed partition and dynamic partitions, the algorithm is easy, but this one is much more complex. When you add much more complexion in the system, it will have a load. We have a heavy load, meaning that they have to do we call it a computational load. Of course, there's a trade-off. You have a optimized memory management, you improve throughput, but you also increase the computational load. The crucial factor is the timing of the compaction. When and how often should it be done? Okay. So there are three options for the timing of the compaction. One approach is to do when a certain percentage of memory becomes busy. System of memory becomes busy 70%. The disadvantage of this approach is that the system will incur unnecessary overhead if no jobs were waiting to use the remaining 25%. So one approach to do when it's certain percent. So if like 75% memory utilization reach, so you start the relocation. But let's say it's idle, so 25% will become wasted. The second approach is to compact memory only when there are jobs waiting to get in. This will entail constant checking of the entry queue, which might result in unnecessary overhead and slow down the processing of the job system. This on demand. Constant checking. You have to do constant checking. You waste, working load. You increase the working load. Constant on demand. And there are three options for the timing of conversion. A third approach is to do after a prescribed amount of time has elapsed. If the amount of time chosen is too small, the system will spend more time on compaction than on processing. So you set a timer. Set a timer. So if like the job processing is like exceed this time, you will activate the compaction. If you the if you set time chosen is too small, you set the time given before you activate the compaction is small. The system will spend more time compaction than on processing. If the amount of time is too large, too many jobs will congregate in waiting queue, and the method of compaction are lost. So there is a trade-off. If time chosen or time setting is too small, there is more compaction than processing. But if the time setting is too large, the waiting queue will be increased and the advantage of compaction are lost. The best choice for any system is decided by the OS designer who, based on the job mix and other factors, tries to optimize both processing time and memory use while keeping the overhead as low as possible. Overhead, this is a work if you add more complexity to the algorithm. This is what I call overhead. The working load, computational load, all is overhead. Okay. You want to increase the processing time. You want to optimize memory usage. You also must keep the overhead as low as possible. You must. This is a trade-off. Okay, summary we the system fixed partition, dynamic partitions, and relocatable dynamic partitions. Compaction. You compact all the external fragmentation. Common requirements of for memory management techniques: entire program loaded into the memory, and contiguous storage and memory until job completed. So each place severe restriction on job size sufficient for first three generation of computer which process jobs in batch mode. Turnaround time was measured in hours. Process job in batch mode. Turnaround time was measured in hours. So anything that you want to do at this at our current time, anything program that take hours to complete, is not good. You also have less patience. You also have a less patience if it takes more than hours to compute a simple program. So, but it's sufficient for first three generations. So this is the next class. Programs are not stored in contiguous memory, not as an assignment during job execution. So they have a cache memory and stuff. That's why this is where we call the cache memory, that the processor doesn't need to go to the main memory, go to the cache memory to make it faster.